Every day, millions of people cross massive bridges around the world. They see endless streams of traffic stretching toward the horizon, towering bridge pylons rising into the clouds, and colossal steel structures standing firm against wind waves and the passage of time. Yet very few ever stop to think about the most important part of the entire structure. Perhaps that is not surprising. After all, the most important part of a bridge is often the part that no one can see. It lies beneath the water, buried in mud rock and darkness, far beyond the view of those passing overhead. A modern bridge can weigh hundreds of thousands of tons. Some stretch for dozens of kilometers across vast river estuaries. Others stand in the middle of the sea, where waves and currents are in constant motion. Ultimately, all of that immense weight must be transferred down into bridge piers, anchored deep beneath the water. And that is where a paradox emerges. Human beings must build these foundations in places where they themselves can barely survive. We cannot breathe underwater. We cannot work effectively in powerful currents. After only a few meters of depth, visibility begins to deteriorate significantly. The deeper we go, the greater the pressure becomes and the more hostile the environment grows. And yet somehow, engineers have found ways to construct enormous structures on riverbeds and even in the middle of the ocean. They have created foundations capable of supporting bridges that endure for decades, and in some cases, centuries, against the relentless forces of nature. What makes this story even more remarkable is that these solutions did not appear overnight. They are the result of thousands of years of experimentation, failure, and innovation. It is the story of how humanity gradually learned to conquer one of the most challenging environments on Earth. To understand how modern bridge piers are constructed underwater today, we must travel back to where this struggle first began. Back to the earliest civilizations that dared to challenge the power of water and attempted to build in places that seemed impossible to build at all. Today, crossing a river by bridge is something so commonplace that we rarely stop to think about it. Yet for most of human history, water was one of the most formidable barriers to movement and transportation. A small stream could be crossed on foot. A narrow river could be spanned with a wooden bridge. But as communities grew into towns and towns into great cities, the need to connect lands separated by rivers became increasingly urgent. And it was at that moment that humanity began confronting a problem it had never truly solved. How do you build a structure in the water? At first glance, the question seems straightforward. Simply place a few supports into the riverbed and build the bridge above them. In reality, however, the challenge was far more complicated. Water is not a static surface. It is constantly in motion. Currents continuously carry sand, mud, and stone downstream. Water levels rise and fall with the seasons. Floods can arrive without warning and destroy what took months to construct. Even if a team of builders managed to drive wooden piles into the riverbed, they would still face another equally difficult question. How could they know those supports were actually standing on solid ground? Today, engineers can survey riverbeds using sonar radar and advanced geological instruments. But thousands of years ago, such tools did not exist. To ancient civilizations, what lay beneath the surface of the water was almost an invisible world. They could not see the bottom of a deep river. They could not determine the layers of soil beneath it. And they certainly could not know whether that ground was capable of supporting a large structure. Yet the need for connection never disappeared. From Egypt and Mesopotamia to ancient China, River communities continuously sought ways to cross the waters that separated them from fertile land trade routes and new territories. For centuries, the most common solution was to build bridges in shallow waters or at locations where natural rock formations could serve as foundations. It was a logical approach. Rather than conquering the water, they sought ways to avoid confronting it directly. But eventually, civilizations began to expand at an unprecedented pace. Cities grew larger, trade extended across greater distances. Vast empires emerged requiring reliable routes to move soldiers, food supplies, and goods. Small bridges were no longer enough. Humanity needed larger structures, and that meant moving closer to deeper waters. One of the civilizations that advanced furthest along this path was ancient Rome. The Romans are often remembered for their amphitheaters, aqueducts, and road networks stretching across Europe. Yet few people realize that one of their most remarkable achievements lay in their ability to build near water, and even within it. The Roman Empire depended heavily on maritime trade. Ships carrying grain, olive oil, building stone, and countless other commodities moved constantly between ports. To sustain this vast commercial network, the Romans needed harbors large enough and durable enough to withstand the forces of the sea over long periods of time. That was a challenge far greater than building on dry land. Waves relentlessly battered structures. Salt water accelerated the deterioration of materials. Storms could destroy weak constructions in a single night. If the Romans wanted to build for the long term, they needed a material unlike anything they had used before. And they found it. One of the most important breakthroughs in ancient engineering was a remarkable material now commonly known as Roman concrete. By combining lime with volcanic ash sourced from the region around the Bay of Naples, they created a substance capable of hardening even in seawater. It was a revolutionary discovery. For the first time in history, humanity was no longer merely trying to resist water. It was beginning to learn how to build in its presence. Many Roman harbors still survive in part nearly 2,000 years later. Their endurance stands as a testament to the extraordinary sophistication of Roman engineering. Yet even this achievement failed to solve the greatest problem. The Romans could build coastal structures. They could create durable harbors. They could significantly improve the longevity of construction materials. But they had not truly conquered the underwater environment in the modern sense. The deeper they went, the more difficult everything became. The currents grew stronger, visibility became worse, transporting materials became more complicated, and most importantly, builders still depended entirely on what they could access from above the water's surface. For centuries afterward, engineers across the world continued improving bridges, harbors, and riverside structures. Yet they remained constrained by the same adversary their predecessors had faced: water. Not because it was too powerful to resist, but because it existed everywhere they wanted to build. Each time a project pushed closer to deeper waters, old problems returned in new forms. Currents undermined foundations. Soft sediments destabilized structures. What happened beneath the surface remained largely a mystery. And then, after thousands of years spent trying to adapt to water, a bold new idea began to emerge. Perhaps humanity had been approaching the problem the wrong way from the very beginning. Perhaps the goal was not to learn how to build underwater. Perhaps the first step was to remove the water from the place where construction needed to occur. The idea sounded impossible, yet it would open the next chapter in the history of engineering and fundamentally transform the way bridges were built, because the war against water was about to enter an entirely new phase. For thousands of years, humanity tried to adapt to water. Bridges were built where rivers narrowed. Natural rock formations were sought out as foundations. Stronger and more durable materials were developed to withstand currents and waves. Yet no matter how far technology advanced, there was always a limit that proved remarkably difficult to overcome. Human beings still had to build from above the water's surface, which meant they were still playing by nature's rules. And nature usually won. Imagine being tasked with constructing a bridge pier in the middle of a major river. The foundation must be placed several meters below the surface. Currents continuously carry mud and sediment through the construction site. Water levels can change from day to day. After heavy rainfall, the entire work area may be submerged. Even with sufficient labor materials and experience, one fundamental problem remained unsolved. How do you accurately build something you cannot see? For centuries, this was a challenge with no perfect solution. Then engineers began to approach the problem from an entirely different perspective. If water was the greatest obstacle, then why not remove it? At first glance, the idea sounded almost absurd. How could water be removed from a river? How could a dry workspace be created in the very place where water flowed every second? Yet that idea became the foundation of one of the most important innovations in the history of bridge construction, the Cofferdam. Today, the term may be unfamiliar to most people, but without cofferdams, many modern bridges might never have existed. At its core, a cofferdam is a temporary structure built to prevent water from entering a construction site. Rather than attempting to work underwater, engineers create an enclosed space around the area where construction must take place and then pump the water out. The result is something that seems almost impossible. A section of the riverbed suddenly becomes dry land. For the first time, engineers can stand directly where the foundation will be built. They can excavate soil, inspect geological conditions, install reinforcement, and pour concrete, just as if they were working on dry ground. The significance of this breakthrough was not merely convenience, it was control. In construction, the ability to control the environment often determines whether a project succeeds or fails. Once water is removed from the work area, many uncertainties disappear along with it. Engineers no longer have to guess what lies beneath. They can see it. They no longer have to speculate about the stability of the ground. They can examine it directly, and they are no longer forced to rely entirely on changing weather conditions from hour to hour. It was a revolutionary step forward, yet the idea was far simpler than its execution. Keeping water out of a small area in the middle of a river is nothing like building a wall in a backyard. Water pressure constantly seeks out every gap and weakness. Currents continuously push against the structure. The appearance of even a small vulnerability can allow water to rush back inside. That is why cofferdams are typically constructed using rows of steel sheet piles or timber piles driven deep into the riverbed. These piles are connected together to form a sealed enclosure around the construction zone. Powerful pumps then operate continuously to remove the remaining water. What emerges afterward is often astonishing. In the middle of a flowing river, a dry workspace appears as though someone has carved a piece of water out of nature itself. It is a sight that earlier generations of engineers could scarcely have imagined. Thanks to the Cofferdam bridge construction entered a new era. Projects were no longer completely restricted to shallow waters. Larger foundations could be built with greater precision. Bridges themselves began to grow longer and more ambitious. But the history of engineering follows a fascinating pattern. Every time humanity solves one problem, it creates even greater ambitions. And greater ambitions almost always create new challenges. By the 19th century, the Industrial Revolution was transforming the world at breathtaking speed. Cities expanded at an unprecedented rate. Railway networks stretched across entire nations. Commerce exploded. The demand for larger bridges continued to grow. Engineers no longer wanted to cross small rivers. They wanted to span the largest rivers, the widest estuaries, the busiest waterways. And that was when the limitations of the cofferdam began to reveal themselves. In relatively shallow water, cofferdams worked exceptionally well. But as depths increased, everything became significantly more difficult. Greater water pressure demanded stronger structures. Construction costs rose rapidly. The amount of material required grew exponentially. Eventually, there came a point where building a massive cofferdam became too complex, too expensive, or simply impractical. The challenge became even more severe in locations with powerful currents. Every second, thousands of tons of moving water exerted force against the temporary structure. A single mistake in design or construction could lead to disaster. And even when a cofferdam functioned perfectly, it could not change one fundamental reality. Human beings were still attempting to transform an underwater environment into a dry one. In other words, they were still avoiding direct confrontation with the water itself. For a long time, that was enough. But then came the largest projects of all, bridges with spans, unlike anything the world had seen before. Structures requiring foundations to be placed at depths where traditional methods were beginning to fail. Projects in which constructing the cofferdam alone became a monumental challenge. Engineers realized that if they wanted to continue expanding the limits of bridge construction, they would have to change the way they thought once again. Perhaps the solution was not to remove the water. Perhaps it was time to accept its presence. And if that was the case, humanity would have to do something it had spent thousands of years trying to avoid. Work directly on the riverbed, not inside a space that had been completely dried out, but at depths where the pressure of the water remained only a few meters away at all times. It was an extraordinarily dangerous idea. Yet it was also the idea that would pave the way for one of the boldest chapters in the history of construction. A chapter in which engineers and workers descended beneath riverbeds, entered spaces surrounded by millions of tons of water, and built foundations unlike anything the world had ever seen before. And the price paid for those achievements would sometimes be greater than anyone could have imagined. For centuries, cofferdams enabled engineers to achieve important victories in their battle against water. But by the 19th century, as industrial cities expanded at an unprecedented pace, human ambition once again began to outgrow the capabilities of existing technology. Bridges grew longer, the rivers that needed to be crossed grew wider, and the world's largest economic centers all sought to be connected by structures unlike anything that had ever existed before. The problem was that the best locations for building bridges were often the most difficult places to build. The water was deeper, the currents were stronger, the volume of passing river traffic was greater, and the ground beneath the riverbed was often far more complex than anything engineers could observe from above. That was when a new question emerged. If completely removing the water was no longer practical, was there a way for human beings to work directly on the riverbed itself? Today, the idea sounds extraordinarily dangerous. But for 19th century engineers, it was almost the only option if they wished to continue pushing the boundaries of bridge construction. The solution they developed was known as the pneumatic caisson, and it quickly became one of the boldest technologies ever employed in the construction industry. At its core, a caisson was a massive structure fabricated in advance and then lowered into position at the construction site. Its bottom remained open while its upper section was sealed. Compressed air was then continuously pumped into the chamber. What happened next was remarkable. The pressure of the air began forcing the water out. Instead of pumping the water away as a cofferdam did, engineers used air pressure itself to prevent water from entering the workspace. The result was a dry chamber created directly beneath the riverbed, not above the water, but beneath it. It was an idea that seemed almost counterintuitive. A room constructed beneath a river with millions of tons of water overhead, yet dry enough inside for workers to stand and carry out their tasks. To the world of that era, it was a genuine engineering marvel. But from that very moment, new challenges began to emerge. To enter the caisson, workers had to pass through specially designed pressure chambers. The air inside the working area was maintained at a pressure far higher than that of the surrounding environment. The deeper the excavation progressed, the greater that pressure became. At first, many believed this was merely a minor inconvenience, But they soon discovered that the human body was not designed to live under such conditions. Yet before those risks were fully understood, major bridge projects had already begun on a scale never seen before. One of the most famous examples emerged in New York City during the late 19th century. At the time, Manhattan and Brooklyn remained separated by the East River. Trade and transportation between the two sides were growing rapidly, while existing means of crossing could no longer meet demand. City planners envisioned a colossal bridge linking the two shores, not merely a large bridge, but the longest suspension bridge ever built at that time. That project would eventually become the Brooklyn Bridge. Today, the bridge stands as one of New York's most iconic landmarks. But during its construction, it was a gigantic experiment involving challenges that no one had ever attempted before. Engineers understood that the immense bridge towers would require extraordinarily stable foundations. And to create those foundations, they were forced to excavate deep beneath the riverbed. The caisson became the only tool capable of making that possible. Enormous wooden structures were lowered into the river. Compressed air was pumped inside. Workers entered and began digging. With every shovelful of earth removed, the entire caisson gradually sank deeper. The more they excavated, the deeper the structure descended. And the deeper it descended, the greater the pressure under which the workers had to operate. The ultimate goal was to reach a layer of ground strong enough to support the enormous weight of the bridge above. It was an extraordinarily demanding job. Inside the caisson, conditions were often hot, humid, and suffocating. The noise of machinery echoed through the confined space. Lighting was limited. Workers spent hours under pressures that very few people had ever experienced before. And then a strange phenomenon began to appear. Some workers, after leaving the caisson, experienced severe pain in their joints and muscles. Others suffered dizziness or disorientation. Some developed far more serious symptoms: paralysis, convulsions, even death. At first, no one truly understood what was happening. Doctors proposed a variety of theories. Some believed exhaustion was the cause. Others suspected that the air quality inside the caissons was responsible. But gradually, a clearer picture began to emerge. The problem was not going down. It was coming back up. When working under high-pressure, nitrogen from the air dissolves into the bloodstream in greater quantities than normal. If workers return to a lower-pressure environment too quickly, that nitrogen can form tiny bubbles inside the body. Today, this condition is known as decompression sickness, or the bends. But in the late 19th century, it remained largely a medical mystery. Many people paid a heavy price before its true cause was understood. During the construction of the Brooklyn Bridge, dozens of workers suffered from the condition to varying degrees. Some never fully recovered. Even the project's chief engineer, Washington Roebling, was severely affected after repeatedly entering the caissons to supervise operations. The long-term health consequences left him unable to continue working directly at the site as he once had. It was a powerful reminder of the cost of progress. Today, when we see enormous bridges stretching across great rivers, we often think only of the finished achievement. We see steel concrete and impressive architectural forms. Yet behind those structures lies the story of men and women who worked in conditions that most of us can scarcely imagine. They entered chambers surrounded by water on every side. They labored for hours in high-pressure environments, and they carried out tasks that no one could say with certainty were even possible. Because of their efforts, the construction industry gained invaluable knowledge about pressure geology and foundation engineering. Those lessons would later be applied to countless projects around the world. Yet alongside those successes, another question gradually emerged. Did human beings really need to go down there at all? The caisson had opened a new chapter in the history of bridge construction. But it had also revealed the clear limitations of relying on human labor in extreme environments. As the 20th century began, machines grew more powerful. Surveying technologies became more accurate. Construction equipment became increasingly sophisticated, and for the first time, engineers began to see the possibility of building enormous foundations without forcing human beings to confront deadly risks at the bottom of a river. The war against water was not over. But from this point forward, humanity's role in that battle was about to change completely. The war against water was not over. But from this point forward, humanity's role in that battle was about to change completely. By the beginning of the 20th century, engineers had learned a difficult lesson. Human beings could work beneath rivers and harbors, but doing so came with enormous risks. The era of pneumatic caissons had demonstrated what was possible, yet it had also revealed the physical limits of the people inside them. The future would belong to machines, not because machines were stronger than water, but because they could survive where humans could not. Today, before a single bridge pier is built, engineers begin with something that would have seemed almost magical to their predecessors. They map the invisible world beneath the water. Modern survey vessels travel across rivers, estuaries, and coastal channels, carrying sophisticated sonar systems capable of creating detailed images of the riverbed. Instead of guessing what lies below, engineers can now identify layers of sediment, buried rock formations, and even hidden obstacles long before construction begins. In many projects, geological samples are taken from dozens of locations. Specialized drilling rigs extract columns of soil and rock from deep beneath the riverbed. These samples reveal information that is critical to the design of the future bridge. How thick is the mud? How deep is the bedrock? How strong is the material that must ultimately support thousands of tons of concrete and steel? Only after these questions have been answered can the real construction begin. And unlike previous centuries, the goal is often no longer to create a dry workspace. Instead, modern engineers frequently build directly through the water. One of the most common techniques involves driving enormous steel piles deep into the riverbed. These piles can reach lengths of several dozen meters. Some are hammered into place using hydraulic hammers so powerful that each strike delivers energy comparable to a small explosion. The process appears deceptively simple. A floating crane positions the pile, the hammer begins striking, and slowly, meter by meter, the pile disappears beneath the surface. What cannot be seen is what matters most. Below the riverbed, the pile continues descending until it reaches material capable of carrying the required load. Sometimes that means dense sand, sometimes compact gravel, and sometimes solid bedrock itself. But modern bridge foundations often go even further. For many of the world's largest bridges, engineers use drilled shafts, sometimes known as bored piles. Rather than forcing a pile into the ground, enormous drilling equipment removes soil and rock from a carefully controlled cylindrical hole. These shafts can reach astonishing dimensions, several meters in diameter, dozens of meters in depth, large enough for an entire room to fit inside. Yet creating such a hole underwater introduces a new challenge. The surrounding ground constantly tries to collapse inward. To prevent this, engineers use temporary steel casings or special drilling fluids that stabilize the excavation until concrete can be placed. And then comes one of the most remarkable moments in modern foundation construction. The concrete is poured underwater. At first, this sounds impossible. Concrete and water seem like natural enemies. Surely the water would wash the mixture away before it could harden. But engineers developed a solution known as the Tremie method. A long pipe extends from the surface all the way to the bottom of the excavation. Concrete is pumped through the pipe and released from the bottom upward. Because the fresh concrete emerges beneath the existing material, it gradually displaces the water rather than mixing with it. The result is a solid foundation formed entirely below the surface. No diver is required. No worker needs to stand at the bottom. The process is controlled from above with extraordinary precision. This approach has transformed bridge construction around the world. Projects that would have been nearly impossible during the age of caissons can now be completed with far greater safety and accuracy. Yet even modern technology faces challenges when projects move into deeper and more hostile environments. Some of the most ambitious bridges on Earth stand not above rivers, but above open water. In these locations, engineers must contend not only with currents, but with tides, waves, storms, and even earthquakes. One example can be found in China, where massive sea-crossing bridges stretch for dozens of kilometers across open water. Another can be seen in Japan, a country where bridge foundations must often be designed to survive both typhoons and seismic activity. In such projects, construction becomes a carefully coordinated operation involving floating cranes, positioning systems, underwater robots, and computer-guided surveying equipment. Increasingly, human divers are being replaced by remotely operated vehicles, or ROVs. These underwater robots can inspect foundations, monitor construction progress, and perform tasks in conditions too dangerous for people. The trend is clear. The deeper engineers build, the more responsibility shifts from human labor to technology. And yet, despite all these advances, the fundamental challenge remains exactly the same as it was thousands of years ago. The water is still there. The currents still move. The riverbed still changes. Nature has not become weaker. Humanity has simply become better at understanding it. That may be the most remarkable part of the entire story. Modern bridge piers are not the result of a single invention or a sudden breakthrough. They are the culmination of thousands of years of accumulated knowledge. Every Cofferdam, every Caisson, every failed experiment, every lesson learned beneath a river. Together they made today's engineering possible, and hidden beneath almost every great bridge in the world is the evidence of that long journey, buried deep below the water where few people will ever see it. When we look at a massive bridge, the first things that usually capture our attention are the elements above the water. They may be bridge towers rising hundreds of meters into the sky, enormous cables stretching across vast distances, or lanes of traffic extending all the way to the horizon. But throughout this journey, we have discovered that the most important part of a bridge is often the part that almost no one ever sees. We began with the ancient civilizations, when humanity first attempted to build near water and discovered that water was far more than a simple obstacle. It was constantly changing, constantly eroding, and constantly making construction far more difficult than it was on dry land. From there, we followed the first major breakthrough with the invention of the Cofferdam, when engineers found a way to create dry workspaces in the middle of a river. For a long time, this innovation allowed humanity to push the limits of the bridges it could build. But as ambitions grew larger, the Cofferdam gradually reached the limits of its own capabilities. That led us into the era of pneumatic caissons, where workers labored under extreme pressure deep beneath riverbeds to create foundations capable of supporting iconic structures such as the Brooklyn Bridge. Finally, we saw how modern technology completely transformed the challenge. Massive machines, advanced surveying systems, and highly precise construction methods now allow engineers to build underwater bridge foundations on a scale that previous generations could scarcely have imagined. And perhaps that is exactly what makes these structures so remarkable. Every bridge is more than steel, concrete, and engineering. It is the product of thousands of years of learning, experimentation, and overcoming limits that once seemed impossible to surpass. Behind every vehicle crossing a bridge lies a long story of human ingenuity confronting the forces of nature. The next time you cross a major bridge, take a moment to think about what lies beneath the water. Because the most extraordinary part of the structure may not be what you can see. It may be the invisible foundations below, silently holding everything in place, day after day, year after year. If you enjoy stories about engineering history and the projects that have changed the world, be sure to subscribe to the channel so you don't miss future videos. And I would also love to hear what topics you would like to explore next. Perhaps the world's longest undersea tunnels, how artificial islands are built, the construction of gigantic mega dams, or any engineering marvel that has always sparked your curiosity. Leave your ideas in the comments below. Your suggestion might become the subject of our next journey. Thank you for watching, and I'll see you again in the next exploration.